All right. So what I'd like you to do is just take a look at this simulation right here. So this, what you're looking at, guys, Jack, please. What you're looking at is the hydrogen atom. This is the hydrogen atom right here. There's one electron in it, and that electron is actually in the first orbit, right? It's in the lowest energy orbit possible. This is called the 1s. Which one of these wavelengths? I have a couple of different options. I can throw a wavelength at it. I could throw a photon at this atom that has a wavelength of 121, 102, or 97. Which one of these has the highest frequency? The 97 would have the highest frequency because the longer the wavelength gets, the less peaks I'll get per second, right? If it's a really short wavelength, I get more peaks per second. So this one right here has the lowest frequency. You with me? What about its energy? Is that highest energy or lowest energy? Highest. High frequency means high energy, right? So this one, 121, long wavelength, low frequency, low energy. So this is the lowest energy photon on here. This one's the highest. So let's throw the lowest energy at it first, and let's see what happens. So I'm shooting a photon at this atom. The electron gets boosted into the n equals 2, and then it falls back down, re-emitting light. So an atom can absorb light, and then it re-emits it. So let me show you again. I throw a photon at hydrogen. This electron in the n equals 1 goes up to n equals 2, falls back down, and re-emits light. See that? Right? So what can a photon do to an atom? What's the take-home message? It can move electrons, right? In fact, if it's high enough in energy, like a gamma ray, if that hits an atom, it actually does something called pair production. It creates an electron and a positron. In this case, it's just going to move an electron. Remember that photons have momentum. They move things, right? So that's what's happening to this electron. It's getting moved by light to the next orbit. Why doesn't it stay in the next orbit? Yep. It wants to get closer. It wants to get close to the nucleus, exactly. And that lowest energy orbit is open. There's nothing there, so it falls back down. It's like a boomerang, right? It goes up for a moment, but it wants to come back. It's being attracted to the nucleus. With me? So we can give it enough energy for a moment, but it will naturally just come back down. We're talking microseconds. So I'm going to hit it with this higher energy photon. Let's say the middle one. All right, 102 is a little bit higher in energy. What's going to happen to that electron? What do you think? In the last example, it went up to n equals 2. If I give it more energy, what would happen? N equals 3, right? So I throw a photon at it. The electron gets boosted to n equals 3, comes back down, re-emits light. All right, if I hit it with the highest energy one, what do you think will happen? It'll go higher, right? Hit it with more intense energy, boosts to n equals 4, falls back down, eventually to the ground state. Eventually. Okay? So the idea here is this. This right here, this original orbit, you need this wording. This original orbit's called the ground state. Right? It's the ground state for that electron. These orbits that it's getting pushed into, those are called excited states. Excited. So, like, let's say it was in n equals 2, because it got hit by a photon and went up to n equals 2. That would be the excited state.
So, like, increasing electron.
Yeah, if you give it a little energy and it goes up to n equals 2, that's an excited state. It's temporary. It's not going to stay there. That's called the excited state. With me? All right. So, here's what happens. Jack? Because this is wavelength. And wavelength and frequency are indirectly related. So the longer the wavelength, the less peaks per second you get. So the frequency is lower. And frequency is directly related to energy. So if you have a low frequency, you have a low energy. It's like a two-step problem. Okay? So anyway, let's move on. So here's what happens in a real atom. What happens is that you get this, if I hit a hydrogen, for example, I hit a hydrogen atom with energy, with light energy, it will absorb it. An electron will get boosted, for example, from n equals 2 to n equals 3, fall back down, and emit light energy. So let me show you in this format, just so I can write on it. All right, so take a look here. This is what you've got on your page in front of you, right? So if I have an electron occupying this orbit, let me do that in another color. Let's say I had an electron, black's good. Say I have an electron orbiting right here in this n equals 1. This is the hydrogen atom, so I've got hydrogen. This is a 1+ charge in the nucleus. All right, there's a 1+ charge in the nucleus. This electron is attracted to that nucleus, right? And that's why it's in the lowest energy state. It would be very hard to remove this electron. If I hit this atom with light, what happens is this electron gets boosted into the next higher orbit. So it gets boosted into this excited state. It will fall back down because it's attracted to the nucleus, and when it does, it releases this red light. This red light is called alpha. This thing is actually what astronomers look for in distant stars. If they look at a distant star and they see this wavelength of light, they know that that star contains hydrogen. So what am I suggesting? I'm suggesting that hydrogen has a unique set of colors that are visible when I hit it with light. Are you with me? If I hit hydrogen with enough energy, I get just specific bands of light release. And what does that tell me about its electronic structure? It tells me something very specific, right? It tells me that an electron is moving from the third orbit to the second. When an electron moves from the fourth to the second, green light is emitted. When an electron falls from the fifth to the second, blue light is emitted. And I can see all these with my eyes, right? If I pass these colors tomorrow, we're going to observe it. Right? I'm going to heat hydrogen up in a lamp for you. It will emit all this light. You'll look with a spectrometer, which is just a prism. It will separate the light out, and you'll see these distinct colors: red, green, blue, and purple. Okay, violet. So tomorrow, you'll actually see these. You're going to directly observe these colors. Okay? You're going to directly observe these colors tomorrow. And the idea is that you can actually tell me what the energy of these orbits is just by knowing these colors. So that's what I'm about to do for you right now. That's the notes you're taking. Yeah.
So, how do you, hit something with a photon?
Just shine light on it.
So I literally just shine light on something that's going to be like,
Yep.
yo, got that.
Yep,
Red.
absolutely. Yep. Have you ever seen bioluminescent, creatures in the ocean? There's phytoplankton that are bioluminescent. Well, they're being struck by, in that case, usually it's chemical. But in some cases, anything absorbs light, it can give light off. That's what black body radiation is. Remember black body radiation? We talked about that. If you hit a rock with light all day long, and then the sun goes down, it's still hot. It's not just hot because the rock's atoms are moving, vibrating. It's actually hot because it's emitting infrared radiation back into the atmosphere. That's part of what that heat is. Yeah, you're just going to shine a light on it. So let's do the calculations. All right. So if I have an electron in n equals 2 in hydrogen, and I give it enough energy, it'll bounce up into the n equals 3. When it falls back down, it emits this red light. What's the energy of that red light? We could do a series of calculations. We could say, this is really 6.56 times 10 to the minus 7 meters, right? And then we could stick that into this equation. C equals the speed of light equals the wavelength times frequency. I could find the frequency, and then I could calculate the energy of that wavelength using E, energy equals Planck's constant times the frequency. You could do that. If you want max points in the lab, hold the questions to the end. Okay. If you want max points on the lab, this is what you'll do. You'll take this wavelength, you'll calculate the frequency, and then find the energy of the wavelength. If you don't want to go above and beyond, that's fine. Just go to this simulation. Go to this simulation. It's called Planck's constant. I've linked it to your lab document. All right. And here I can just click on the wavelength. The wavelength is 656 for that red light. So I'm just going to click on 656. Now you can see the energy is 3.01 times 10 to the minus 19 joules. With me? So all I have to do to find out the energy of a wavelength is just go to this simulation, click on the wavelength, and I'll get the energy. You don't have to do those calculations. That's to go above and beyond. All right. So let's come back here. If I know that the energy of that photon, is 3.01, let's see, let me write it right here. The energy of that photon is 3.01 times 10 to the minus 19 joules. Good? Got it? So that's the energy of that photon. If I know that, here's all I have to do. If I want to know, I'm going to tell you to start off with that this energy level, n equals 2, I'm just going to tell you its energy. You ready? That energy is negative 5.45 times 10 to the minus 19 joules. All right? So 5.45 times 10 to the minus 19 joules. That's the energy level of this second orbit. We're calling this the ground state. Okay, so this is the ground state. All right, so if I want to know the energy, my goal is I want to know the energy of this excited state. What is the energy of this excited state? That's my question. And all I have to go on is what the color is that was emitted when I heated it up. That's all I have to go on. So here's what you'll do. If you notice, all I have to do is subtraction to figure that out. This represents the energy change right here, that color. So all I have to do is subtract. That's it. So this is your formula. You ready? I'll write it out in words so you can understand it easier. All you're going to write is the energy of this excited state that's going to be equal to the energy of the ground state minus the energy of the light emitted. All right, so it's just subtraction. It's just subtraction. Yep. Good question. Let's say that I release a free electron right now. It has zero energy, and it's attracted to this proton in the nucleus, right? It will get attracted to the nucleus, right? It gets attracted to the nucleus through the electromagnetic force, and it releases energy. In this case, it's hydrogen. It releases exactly negative 13.6 electron volts. So it would be negative 13.6 because I'm telling you it's released. That's what the negative means, right? If I wanted to break that electron away, Cassie, if I wanted to break that electron away from the atom, I'd have to apply exactly how much energy. I'd have to give the system how much energy. I want to remove that electron. This electron, I want to remove it. How much energy would I have to give it? 13.6, positive 13.6. Now I'm telling you, I have to add that energy in order to break that system apart. So the idea is, the more negative, the more stable that situation is. Because I have to add more energy to the system in order to break it apart, to destroy that system, right? So every time you add energy to a system, positive. Every time you get energy out, like an emitted photon, negative, right? So here's what we're doing. For this case, if I want to know the energy of this excited state, all I have to do is say negative 5.45 times 10 to the minus 19 joules, right? That's my ground state, this first energy level, right here. This number right here, that's my ground state energy. And I'm going to subtract the energy from the light emitted, which we said